So everybody say hello to the junior boys. Oh, you don't really seem to care.
How's yours going? Oh yeah, there's no way Jacob's watching.
Yeah, it's okay. Poor Jacob. Maybe he is watching it, and he will prove you wrong. Okay, so question 3. Guys, we're at the bottom of page 134. So we've got a velocity function. So we're just going to do, some of them I have multiple parts. We're just going to do the part that pertains to average value and kind of just talk through any other parts. This part, I only gave you the one. So we've got a particle moving along the x-axis. Velocity is given to you. And I told you the other day about like the position, velocity, acceleration stuff. They usually give you the velocity function because you can do the most with that. So we've got velocity, and then this is an initial condition that you would use in one of the other parts. We don't need it here. So part D says find the average speed of the particle. So when we're talking about average value, this is the formula that you'll be using every single time. So the average looks like that. And then like this function, f of x, the stuff that goes in the integrand is whatever they tell you to take the average of. So if they tell you to take like the average position, you plug in a position function. If they tell you to take the average temperature, you plug in a temperature function. So if they're telling us to take the average speed, we should be plugging in a speed function. And they're going to give us the interval so we can set up like the a and b and all that stuff. So we'll have 1 over, and what will the b minus a be? 2 minus 0. We've got our interval. So this is the width of the interval, which is 2. Bounds? 0 to 2. And then what's speed? Absolute value of velocity. Good. You guys remember, especially physics people, velocity does have a sign. So like you can have positive velocity and you can have negative velocity. Speed, a sign is never mentioned. There's no direction with speed. It's just speed. So this would be absolute value. And then on the AP test, all you have to do is you just write it like this. And then they're expecting that you will plug it into your calculator. So you don't even have to write the natural log function out, because this right here is them like giving you a key and saying like, all right, if you write v of t, you mean this function. So you can just write it right here. Make sure it's in absolute values. And then question 3, when this test was released, question 3 was still on the calculator section. Question 3 for you guys will be on the non-calculator section. It used to be 3 and 3, now it's 2 and 4. So you guys will have 2 calculator, 4 non-calculator. So this, back when this test was released, was still on the calculator section. So just to show you guys what this looks like, we would plug in this part. We'd have 1 over 2 out front. And then in our calculus menu, numerical integral. And then it looks exactly like the way we write it down. So you should be able to find kind of where everything goes. So 0 up to 2. And then on the Inspire, right next to the 9, you know that like weird menu of templates? It's right next to the 9, so if you press that button, it actually also has an integral. Where is it? Oh, it's right down there. So it's got all sorts of things. So it has an integral there. If you want to find it there, that works. So we take the absolute value and then type in our velocity function. So it is the natural log of t squared minus 3t plus 3. And then our differential would be t. Make sure you're matching the variable. You can change it to x if you want to when you're typing it in. Just make sure you match it in the differential. So this is our approximation. Quick note, if you have decided that you are a truncator, because we talked about you can be a truncator, you can be a rounder, I don't care. If you are a truncator, ladies, if you are a truncator, what are we writing? 0.370. You still need that 0, even though it's a 0, because they need 3 decimal places. So even if it's a 0, you need it in there. So rounder, truncator, whatever, it'd be either 0.370 or 0.371. You guys know I'm a rounder. So that would be your final answer. So like on the AP test itself, you would have points for the setup, probably 2 points for the setup and then 1 point for the answer. And that way, as long as the setup's right, like you may have plugged something into the calculator wrong at some point, you just wouldn't get the answer, but you would still get the points for the setup. Yeah?
We don't have to give units unless they give us units.
Right, so you wouldn't just like make up units. If they tell you that the velocity is given in meters and they mention the time as seconds, then you would say that the average speed is in meters per second. But yeah, unless they mention the units. And actually, they, in the very next one, if you guys flip, they'll mention, so like part A on this next one, they said find f prime, and then they said indicate units of measure. So most of the time, if they want the units, they will throw in a sentence like that. Okay, so we're looking at this one. This one's question 4. Question 4 is non-calculator. So everything that we're doing here, we're doing completely by hand. So we're just going to do part D because that's the part that asks for an average, but we're going to kind of talk through what the other 3 parts would be, and kind of how you would do them. Not actually going to do them, but just so you guys get your head wrapped around what they're actually asking. So if we look, it says that this is a rate. So this whole function that they've got written here is a rate at which calories are burned. So the number of calories per minute. So this little piece right here from 0 to 4 is given by this function. And then it says it's piecewise linear. So the rest of the time it's either horizontal lines or like linear pieces like that. So it's already a rate. It's given in calories per minute. The units are right here. So for part A, if they're asking you to find f prime of 22, how would you find that? It's like this already is f. Keep that in mind. Remember a funny looking graph? I told you you need to know what it's a graph of in order to answer the question properly. So if this is already f, based on a graph and a graph alone, how could you find this? Slope. It's a slope. If you're given a function, you would take the derivative, but if you're given just a graph, it's just the slope. So we're looking like on this line, so 22 is like right here, and you could just use this point and calculate the slope because it's sitting on a linear piece. The slope is the same the whole way. So we could find the slope, and then it says indicate units of measure. What would the units be?
Minutes. Calories per minute.
Calories per minute. Because this would be, you know, slope is like change in y over change in x. The y functions are calories per minute. The x functions are minute. So it'd be calories per minute per minute. So like how that rate is changing as time goes on. All right, so that's part A. It's just a slope thing. This, remember, the physical representation of a derivative is a slope if you're looking at a graph. Part B, it says at what time is f increasing at its greatest rates? So you should be able to just actually look at the graph and answer that for me. So what are we looking for on the graph? When it says when is f, and this is f, when is f increasing at its greatest rate? Steepest slope. Good, we want the steepest slope. Any guesses? What about 2? It actually does end up being exactly 2. So like this isn't increasing, this isn't increasing, this is increasing, this and this are not increasing. What's steeper, this segment right here or part of this segment right here? Part of this one is steeper. So this one, you could actually go through and do the calculations by hands, like taking this, taking the derivative. You would actually have to take the second derivative because if f is increasing, that's f prime. If we want it to be increasing at a greatest rate, that means we want to maximize f prime. So to maximize f prime, you'd have to take the second derivative. Okay, and this right here, notice anything special about that point? Anything changing in the graph right at that point? Change in concavity. That's an inflection point. Do you guys remember the 3-column chart that I had you make? So in the 2 columns, it says that your function would have an inflection point at the same time that a derivative would have a max or min. So this function has an inflection point, and that means its derivative is having a max. That's the steepest slope right there. So you would actually calculate it by hand. Just do the derivatives, and then it does end up being 2. The reasoning that supports your answer, that's what they mean, is they want you to show work. Part C. Find the total number of calories burned over the interval 6 to 18 minutes. Any thoughts on that? This is a rate. It would be area. Good. So this is the rate. This is calories per minute. If we wanted the total number of calories, we would take the integral, which is an area, if we're just looking. So it would just be area under the curve between 6 and 18. So it would be like here. It's like this whole area in here. We're actually going to do this. So this, I think the easiest way to split it would be a rectangle and a trapezoid. So this rectangle right here is, what is this, 12 units wide and then 9 units high. So 12 by 9, we've got 108. And then this piece up here is a trapezoid. You could split it, I mean, you can do whatever you want with it. Like if you're more comfortable with like a triangle and a rectangle, it doesn't matter. It's like we can make, here you go. You guys might be more comfortable with that set of trapezoids. So this rectangle is 2 units wide by 6 units tall, so that's 12. And then this triangle is 4 units wide, 6 units tall, but we're only taking half of it, so that's another 12. However you want to split it up, whatever you need to do to get the area. And notice it doesn't say show the work that leads to your answer, so you just need an answer. So this would be 132 calories. Okay, good on that? Okay. So part D is the part that actually mentions the average. So this is a little bit different because they're giving us a function and then asking us to like solve for part of the integrand. And so they want the average to come out to be 15. So it's kind of going backwards, like we're gonna be figuring out what should be in the integrand. So we're gonna set up the average value formula. So here's our time interval. So you've got 1 over, what's the length of the time interval? 12. And then our bounds, 6 to 18. And then just looking at this, like reading through, what is the integrand gonna be? We're trying to find the average of the calories per minute. And according to this little change that they just made, how many calories per minute are being burned? Not a number, function, expression. F of t plus this right here. That's what they're telling us is the number of calories that are being burned. It said some setting was changed, so now that's the function that represents how many calories are being burned. So that's what goes in there, because that's what we're trying to find the average of. So whatever you're trying to find the average of goes in the integrand. So it'd be set up like this. But this is actually an equation. We'd say it equals what? Equals 15, good. So this one's a little bit strange because we want to solve for C. So this is almost algebra in a sense, like we're just trying to get the C by itself. So we're trying to solve for C. So whatever you need to do to get the C by itself. So what could we start with? Can't subtract the 15. We're actually trying to get things away from that. Oh, can't subtract the f of t, no, because it's inside a function. Multiply by 12, let's clear that out at least. And then any thoughts on something we might want to do with that integrand? We're trying to solve for C. Can't take a derivative. Are we trying to solve for this? Are we trying to solve for this? Okay, so we preferably would like them not together.
Split them up.
Split them up. Separate the integrals. We're having a tough day today. Everyone that keeps like whispering their answers and I'm sitting there like trying to figure out if you said it or not, literally the worst thing that can happen is you say the wrong thing. Like I don't think we shame people for wrong answers in here. Okay, and then what is this? 180. All right, now what? What's this? Yeah. If you see an integral, it represents an area. We just found that in part C. They do this all the time. Like they'll constantly build on what they just asked you to find. We just found this. What was it? 132. You should be able to just look at this and tell me what C is. What's the time interval? 12 minutes. 4. Good. Time interval is 12 minutes. What's C? Like if I were to graph C, what would it look like? Right? Horizontal line. So we don't know what the horizontal line is. We know what the interval is. It'd be a rectangle, right? So a rectangle, how wide is this rectangle? 12. So what we're saying, because this represents how many calories were burned on that time interval, right? The time interval is 12 minutes, and a total of 48 calories were burned.
Okay, yeah. But we should know.
So 4 per minute. That's why I say things like you should be able to just look at it and tell me.
We should. I just can't right now.
Okay, so C is 4. So whatever setting was adjusted, it means that they burned, on average, 4 more calories per minute. So that's what we're looking for, is that value of C. Okay, questions on this one? No, good. Okay, let's look at question 6. Same thing, really the only one we're doing is this part D, but I want to at least have you guys familiar with what you'd be looking at here. We have 2 different position functions. They're both traveling along an x-axis. We've got particle P, particle R, they each have their own position function. So start off with part A. So part A says, find out the times T during which particle R is moving to the right. So if you have a position function, how would you find out when the particle is moving to the right? What's that? When what's positive? When the derivative, yeah. What does the derivative represent? Velocity. There's so, like, I have to have really good ears to hear you guys that are whispering the right answers. Velocity. Velocity. So you know derivatives. Derivatives take you from position to velocity, from velocity to acceleration. Antiderivatives go back in the opposite direction. So if our velocity is positive, that means the particle is moving to the right. Negative velocity would mean what?
To the left.
Moving to the left. No velocity.
It's either standing still or it's changing position or changing direction.
Right. So like even that, if it's changing position, like instantaneously, it would have a moment where it's still. Good. So moving to the right, we would take R prime and we would find where it's positive. So ideally what you'd do is you'd take the derivative, set up a sign chart. And then once you have that sign chart set up, you would see like, oh, it's moving to the left during this interval, and it's moving to the right during this interval, and then oh, back to the left. Whatever it is, you'd have a sign chart set up for R prime. And that sign chart will tell you when R is moving to the left versus moving to the right, when it's changing directions, things like that. So how about part B? Part B is really similar. How could you find out when the 2 particles are traveling in opposite directions?
Double sign chart.
Double sign chart. Good. We would set up a sign chart for R prime. That'll tell you when R is moving left or right. We'll set up a sign chart for P prime, which will tell you when that's moving left or right. So what we're looking for is when P prime and R prime are what? Opposite signs. Good. Okay, and C, acceleration. How would I find acceleration? Good, double derivative, second derivative. So we already would have P prime, we want P double prime, and then we'd plug in 3. So if you have position, second derivative gives you acceleration. And then this question, I don't know if you guys remember answering it. We did a lot of these back in the day when we learned this stuff for the first time. Is the particle speeding up or slowing down? What's the trick with this one? What do people usually leave out? So I'll tell you the common mistake. Let's say this turns out to be positive. If the acceleration was positive, people just go, oh, it's moving or it's speeding up. Like if the acceleration was negative, depends on the velocity as well. Good. So the signs, if the signs match, it's speeding up. If the signs are opposite, it's slowing down. It's like if velocity is positive, that usually makes sense to people. So if velocity is positive and acceleration is positive, that's speeding up. Like that makes sense to you guys, right? Good on that. So if velocity is positive and acceleration is negative, that's slowing down. And I think that makes sense to people too. It's when the velocity is negative that it freaks people out. So let's say the velocity is negative and the acceleration is negative. Negative acceleration does not mean your particle is slowing down. What does negative acceleration mean? Doesn't mean you're going in the opposite direction. Velocity negative means you're going in the opposite direction. It means your velocity is decreasing. So if your velocity is negative and getting more and more negative, it's actually speeding up because speed is absolute value. If your velocity is negative and increasing, then it's headed towards 0. And if it's headed towards 0, then it's actually slowing down. So you'd have to answer the question of what sign is the velocity, which we'd already know from the sign chart, and then figure out what sign acceleration is. Either they match or they don't, and that would be either speeding up or slowing down. Okay, part D. Here's our average value. So on the interval from 1 to 3, so whatever the interval is, you can set up your 1 over b minus a. So 1 over 2, bounds. 1 to 3. Okay, distance. The distance between the two particles. Any thoughts? I will tell you, it's not that crazy square root distance formula that you guys did probably in geometry. It is not that. Distance between two particles. It wouldn't be an area, because average distance, so all that's going in here is some sort of distance formula. And I think it's easier than you guys are making it. So keep in mind, they're not, because the distance formula that you guys had in geometry was because you could be anywhere on the coordinate system, so they could be like at a diagonal from each other. If they're on the x-axis, they're on the same line. So like one of them could be here and one of them could be here. You're just subtracting one function from the other. What's the catch? There's one extra little thing you have to throw in there. Absolute value. Yep, you need absolute value in there because you'd never say like, oh, they're -2 units apart. The distance is always a positive quantity, so it would be the absolute value, and then you would have P of t minus R of t, or R of t minus P of t. That's what the absolute value is there for, like that. Yeah, so that's the important part, is the fact that they're on the same line. So literally all you have to do is subtract one position from the other, and then throw it in absolute values because distance has to be positive. This is a beautiful thing called write, but do not evaluate. I had a minor short panic attack in first hour because I thought we were going to have to do this by hand because it's a question 6, which is non-calculator. And then I read and saw that it was right, but do not evaluate, and we all felt okay again. So they do. You could. It would just be horrible. Because this, like, we'd have to take the antiderivative of this, which involves a little chain rule, minus this, which is 4 different power rules, and it's an absolute value, so you'd have to set it equal to 0 and find where the x-intercepts are, so you could split all the different pieces up. So it could be done, but it would be horrible. It would be horrible. All right, questions on this one? Guys, stay with me. All right, we've got another page of these, and these are pretty quick, because we've got 2 multiple choice. And then we're going to finish off with the cross-section stuff that we did yesterday. So this one, see if we remember this. This is stretching us all the way back to limits, the part A on here. So is R continuous? And we did this exact problem, but it was in like October, so you guys probably have no recollection at all. But if something's continuous, let's see if we remember this at all. There was a 3-step criteria for something being continuous at a point. I will tell you the first 2. Criteria number 1. The function has to exist at t equals 5, or whatever it is. Function value exists. Number 2, the limit has to exist. What is the third and most important criteria? We already got the limit part covered. The function value exists. The limit value exists. We actually hadn't seen derivatives yet. Say it again.
Like the function value has to equal the limit.
Yes, and they have to be equal. So, function value, did you whisper? Does anyone speak loudly ever? All right, so we would take these, the limit would have to exist, meaning this value would have to be the same as this value as you come to 5 from both sides, and then the function value would be whatever you plugged in here, because that's where the 5 gets plugged in. So if they're all equal to each other, like basically left equals right equals function value, and then it would be continuous. So that's how you do part A. Part B, find the average rate at which. So you see average, we're going to set up our 1 over b minus a formula, and then the rate is what's going in our integrand. What's the catch with this one? We're going from 0 to 8.
Oh, that's not. Oh, wait, just kidding.
What's the catch? It actually doesn't matter to us for this type of problem if it is continuous or not. But if I'm just like setting this up, what formula am I plugging into my integrand?
Oh.
Sort of, yeah, both. How can we use them both?
Oh, 2 separate things.
2 separate things. We've got from all the way from 0 to 8, so we'd have to do 0 to 5 on this one, and then 5 to 8 on this one. Here's the part that people mess up all the time. You know that 1 over b minus a? You wouldn't use 1/5 for this one and 1/3 for this one. You'd have to put a 1/8 and then like big brackets with everything on the inside. People mess that up all the time on this problem. So the whole interval is 1/8, so we would put that out front, and then the sum of the 2 integrals would be on the inside. You will not get the same answer if you do 1/5 times the first one and 1/3 times the second one. It will not come out right. Okay, so first one, we're going from 0 to 5, and we have this first function, but then it's piecewise, so they swap functions. And this one goes from 5 to 8. There we go. All right, I'm not going to plug this in. You guys know how to use calculators. You just plug this in, get the decimal approximation, 3 decimal points. It's question 2, so of course you have your calculator. Okay, we're going to look at these 2 multiple choices as well. They're both on the calculator section. You will notice when you guys are looking at practice exams, not all of the calculator sections actually need a calculator. One of the clues, and you guys may have heard this clue before on the ACT, have you guys heard like standardized test prep advice that if your answers have decimal places, that means you're going to need your calculator to get the answer? Fun fact, if you haven't taken the ACT before, or if you're taking the SAT or whatever, fun fact, on the math section, if you've got decimals, it means that you probably need your calculator to get it. What's that?
They said they could solve all without a calculator.
Oh, not on here. I don't know enough about the ACT to answer that question, but. All right, so 79. Keep in mind with multiple choice, there's no work that needs to be shown. It's just a Scantron that they receive, and the answer is either right or wrong, and that's it. So you don't need to show anything. So this one, particle moves along the x-axis. We've got a velocity, v of t, acceleration, a of t. Which of the following gives average velocity? All right, so we're going to go through one by one, see if we can either eliminate or not eliminate them. How about part A? Does part A look like it would give you average velocity? That would be change in acceleration over change in time. Would that give you average velocity? No, it actually gives you something called jerk, which is the third derivative of position. And it's the way that acceleration changes. I literally, like, I think of that word. Have you ever, like, pressed down on the gas too hard and you, like, physically move?
Oh, yeah. I know exactly.
That's a change in acceleration. If you accelerate too quickly, it will jolt you or, like, jerk your body a little bit. Yeah, so this is actually the average jerk, in case you guys are interested. Not average velocity. So this is out. How about part B? Does that look like it could be average velocity over the time interval? Okay. Never ever circle an answer without looking through the rest of them. It's like we're thinking that B looks good, but we're going to eliminate the rest of them. How about part C?
That looks better. I feel.
Part C looks even. That's speed. Thank you, Eric. That's out.
Never mind. It doesn't move better.
That's speed. How about D?
Wrong.
Wrong fraction. Good. That's not. How about E?
Nope.
Like what is E doing? They're just adding 2 values of velocity together and dividing by 2. So like that's what some people might think an average is, but not. So we're going with B. Question?
I just read somewhere that like the answer that has the most in common with the rest of them is usually the right one.
That is an awesome technique. That's, yeah. Did you guys hear Isabella? That's like an ACT technique as well. She said that she read that the answer that has the most in common with the other answers is most likely to be right because they can kind of fluctuate like little details. So yeah, and this one definitely does. Okay, let's look at 88. This one definitely needs your calculator. All right, so question is, during this time interval, what is the average rate of water flow? Guys, bring it in. Okay, so average rate of water flow, so we can start with 1 over what? 4. Bounds? 0 to 4, and then what's going in the integrand? R of t. Good. So again, like I just said, this is on the multiple choice section. They will never see that you wrote this down. So like if you know what the formula is, you could just plug it right into your calculator and get an answer that way. Okay, so this would be, put a 1/4 out front. There we go. So we type it all in like that, and we get 14.691, which is C.
Oh yeah. Nice.
Okay, that's the last average velocity. Any questions on the average velocity problems? No? Good. It's a formula. If you have that formula memorized and you know how to use it, I think you'll probably be okay. You can see that they ask about it in like every one of these contexts was very, very different from all of the others. The word average is always there. Like hopefully that should stick out to you. All right, let's look at cross sections. All right. So this one, I showed you guys this yesterday when we were looking at the question that we did yesterday, but the same phrase. Here, question 3, part B. The region R is the base of a solid. Flip to the next page. Question 1. The region R is the base of a solid.
Hey, do you think it's the base of a solid?
The next question 1. The region R is the base of a solid.
Why don't they like any of the letters?
And then we got, I don't know. And then we have R is the base of a solid. So we changed things up a little bit, but we got everything under control. You will also, so like that should give you a clue, but they will literally say cross section. They say cross section in every single one of these problems. If you didn't recognize the R as the region, then you should recognize the cross section thing. All right, so flip back to this one. We got this question 3. Do you guys recognize this one? We did part A already. We had to split it in half to get the 2 separate areas. Okay, so here are 2 functions. So read through. Here we go. The region R is the base of a solid. Wonderful. For each y, so your instant clue right there, they've started telling us things in terms of y, which means that this one is going to be all y stuff, y bounds, y functions, dy instead of x stuff. So they tell us that. They mention the interval in terms of y, and then they say the cross section taken perpendicular to the y-axis. You do not have a choice. If they tell you that, you have to do everything in terms of y. There's no other way to get the problem correct. So remember our lines that we drew in? It's like when we drew in lines yesterday, what kind of lines am I going to draw into my shape right now? Horizontal. Good. I have to be in terms of y. So my lines that I draw in will be horizontal. So obviously you can see the length of the line is going to change depending on how high or how low I draw it on my graph. This looks like that. Okay. And it's a rectangle. Okay, so first thing we need to do is kind of set up what our base looks like. We can no longer use y equals the square root of x as this function. What should we use? X equals, wouldn't be the square root of y. It'd be y squared, good. And then this one again, we can no longer use y equals 6 minus x. We'd write it as x equals 6 minus y. Okay, so those are our 2 functions now. It's pretty rare that we see things given in terms of x, so we're not like super comfortable with it. But in this section, it's about half and half that they switch them. Sometimes they switch them, sometimes they don't. The functions will always be this easy to rewrite though. It won't be anything crazy. It'll be just some sort of little polynomial. So those are our 2 functions. So let's go now to the actual cross section. So it's a rectangle. So as soon as you see the shape, I want you writing down like, oh, what's my geometry 101 formula for this? So what is the area of a rectangle? Base times height. Good. So just start with that, and then we'll worry about how to sub everything in. So eventually our area function is going to have to be all in terms of y, like all sorts of y things, because our integrand formula needs to be all in terms of y. So we can write the base in terms of y. They actually just handed us the height. They're like, here you go. Here's the height. What is it? 2y. Good. So we're going to have our base, which we'll fill in just a second, and then the height is always 2y. The only time they can ever give you rectangles is if they give you an expression for the height. Because normally, like if we do squares, a square can only be as tall as it is wide. A semicircle can only be half as tall as it is wide. Equilateral triangles, all 3 sides are the same. So a rectangle, like you could have one base and then the height could be totally, totally different. So the only way that they can do a rectangle is if they give you an expression. So they did, that's the height. So now let's talk about the base. The base would be like here, when x equals like 0.5, the base would be this. But up here at like 1.5, the base would be this. So we should have a formula, an expression that represents what the base is at any given value of y. Any thoughts, ideas? It would be this one minus this one, right? When you're going in terms of y, it's always right minus left. If you're going in terms of x, it'd be the upper function minus the lower function. Because this, whatever this x value is right here, minus whatever this x value is right here, that gives me the length of that line, which represents the base. Or if I move up here, whatever this x value is minus this x value, that gives me the length of that segment. This distance, of course, is changing as y changes because it's given by a function. And this value is changing as y changes. So this line, like this dot that I drew right here and right here, the right segment of any of my horizontal lines are lying on this line, which is 6 minus y. And then minus the left segment of any of these lines is sitting on this equation, which is y squared. Okay, so it's right minus left. If I'm in terms of y, it's right minus left. If I'm in terms of x, it's what? Upper minus lower. Good. It's always the larger. Think if you're going in terms of y, the higher the value is, the larger it is. If they flip it and you have x equals functions, the farther to the right it is, the bigger the x value is. So it's always upper minus lower if x is your variable, right minus left if y is your variable. So that's our area. Are you guys okay with that? So these are the rectangles, but this is based off the shape that they have us sitting on, the region R. So when we set this up, and this is another right but do not evaluate. So the volume equals, everything should be in terms of y. My bounds, my integrand, my differential. So what are my bounds in terms of y? 0 to 2. Good. They actually gave that to us. So it's right in there. So we're going from 0 to 2. And then the integrand is your area function. But it's your area function entirely written in terms of the variable. And that's what we have right here. And then our differential would be dy. And that's all you need to write. And it's actually best if you don't like FOIL or distribute that to y. 2 reasons. First of all, when it's written like that, the AP readers can see all of your pieces. Like they can see the base, they can see the height. And then the other reason, of course, is you might mess it up. And it's worth not simplifying if there's a chance you could mess it up. So that's our final answer. Any questions on this one? No? Good. Okay. We did this one yesterday. This one, let's take a look. We are doing part C. Okay, so again, the region R is the base of a solid. For this solid, the cross-section's perpendicular to the x-axis. So what orientation will my lines be? Vertical. Good. Are semicircles. Okay, anyone remember that formula from yesterday? There's a diameter in there somewhere. 1/8 pi. Good. So let me just, in case we forgot. So what do you, like, what formula do you normally think of for the area of a semicircle? Pi r squared over 2. But this isn't a radius, it's a diameter. So we have to rearrange it so that it's a diameter instead of a radius. So what we did, and we did this in the notes, you don't have to recreate this, I'm just reminding you of where the 1/8 came from. So this is 1/2 pi, and then the radius is half of the diameter, and then that's in parentheses being squared because r is being squared. So this, when I square the 1/2, I get 1/4, and then times this 1/2 that was already there. So I have 1/8 pi, and then the diameter squared, because this line represents the diameter of a semicircle, not the radius of a semicircle. All right. So that, again, you don't ever have to recreate that. If you've got it memorized, you can just use that. So that's our formula. And then it says it extends from y equals f of x to y equals g of x. Find the volume. So when we're actually plugging this in, it's 1/8 times pi. And then what is the diameter? As I move from left to right, my diameter is going to change. It's going to change as x changes. So what formula can I give for the diameter? What's a super generic answer? Like, what do I always give? Yeah, I mean, f minus g, and you can write that. Because if they wrote your functions down, they wrote this here, they wrote this here, that's almost giving you like a key. It's saying anytime you write f of x, I know what function you're referring to. Anytime you write g of x, I know what function you're referring to. So you can write f of x minus g of x, and then in parentheses, squared. Okay, because my diameter will change. Like if I use whatever this x value is right here, it's going to be a different diameter from if I use this x value right here. But if I'm looking for just the length of it, it's going to be whatever this value is minus whatever this value is. Upper minus lower. Okay, so let's set it up. Volume equals, I'm going to put the 1/8 pi out front just because I know I'm allowed to do that with constants. Like you can put them inside, you can put them outside. As long as it's a constant, it doesn't matter. How about my bounds? 0 to something. Right, we couldn't have x. We couldn't use c. We need to know it. We got to find the intersection point. We need to know this point. And we've got our calculators, so let me just refresh you.
Oh,
Oh yeah, you're fine. You're fine. Don't worry.
it all makes sense.
All right, so I'm gonna plug these in. So my first function is 1 plus the sine of 2x. And then you always hit tab if you wanna add in another one. So then we have e to the x over 2. So you can see, like, they didn't even give you a scale at all. So you have no idea how far in there. They're clearly zoomed in pretty far. Because, like, what we're looking at, this whole picture right here, is just like this teeny tiny little sliver of the graph right there. All right, so definitely intersecting at 0. And you could even test that. Like, if I plug in 0 right here, what's the sign of 0? 0, and then plus 1. So that would be 1. If I plug 0 in here, what's e to the 0? 1. So they're definitely intersecting at the point 0, 1. But that almost gives you a little bit of a scale too. If this is 1 unit, this has got to be like just over 1 unit, probably somewhere between 1 and 2. So to find the intersection point on the Inspire, you hit menu, and then this menu is what we're going for, analyze graph and intersection. Just remember you have, if that like dotted line that you can just kind of move side to side. So get it somewhere to the left, and then I'm going to click down, and then somewhere to the right. So it kind of like catches that intersection point, and you're never ever just gonna go off of what it shows, because like mine right now is only showing 2 decimal places. So if this isn't accurate to 2 decimal places, then your final answer can't possibly be accurate to 3 decimal places. So we click, get it highlighted like that, and then you would press the store. It's the variable button right above the 9, and I'm gonna store it in just as A, so that I can use it later. So to actually find out what it is, I would go into a calculator page and just press A, and it'll show me more of the digits. It's set right now to display 6 digits. It's storing a ton of them. It's like you're actually accurate if you do store that number. So it's about 1.13569. And then we would just plug in, and you could write it. You could write f of x minus g of x on the AP test. Don't forget your differential, and then we'll plug this into our calculator. So I'm going to put out front a pi over 8, and then my integral. So from 0, and then for the upper bound, I'm just going to type in a. And my calculator has a stored in every decimal place that it's got. And then another trick, if you have the Inspires, because I have my functions right now in the first tab. So if you hit variable, see how I have the a that I stored, and then I have the f1 and f2 that I have plotted. So you can just grab the f1. It's like f1 of x, and then minus f2 of x, and then square the whole thing. It's like once you have things typed in once, it's super easy to just kind of grab them. Okay, so that would be our setup. The pi over 8, I put it out front. 0 is our lower bound. A is what we just had stored. And then I stored the sine function as f1 on the previous page. And then the exponential function was f2. And I'm squaring it. And this is my teeny tiny little answer. So either 0.077 or 0.078. There we go. Okay, how we doing? You guys are troopers. One more. Got a multiple choice here. So this is on a calculator section. It's 92. So this one, they didn't give us the sketch. We're going to do a quick sketch so we can actually see what it looks like. And so it says it's bounded below by the graph of y equals x squared. So that would be like this. Bounded above by the graph of y equals square root of x. So that looks like this. Okay, so that is that. Do you guys know where they intersect? 1 and 0. Yeah. Yeah, so 1 squared and the square root of 1 are both 1. So they intersect at 1, 1 and at 0, 0. All right, so it says R is the base of a solid whose cross sections perpendicular to the x-axis. So what lines am I drawing in here? Vertical. And then there's squares. Okay, so just start me off with a very generic area formula for squares. Side squared, base squared, perhaps. And then the base changes as x changes. Like this base down here would be different than this base right here. It would be different than this base right here. What formula in terms of x will tell me what the base is at any point? Square root of x minus x squared. Good. The upper function minus the lower function. So it's root x minus x squared, quantity squared. Okay, so volume equals, we're going from x equals 0 to x equals 1, and then this function right here is our integrand. All right, so we have 0 to 1, and then in parentheses I'm going to put the square root of x minus x squared, quantity squared. I'm hoping that I don't need to say this out loud, but we wouldn't even think of like just squaring this and then just squaring this, right? Like x minus x to the 4th. We know that's not how squaring works. Good, okay. All right, so we get about 0.128 or 0.129. There we go. Okay, questions? Concerns about cross-section? Average value? No? All right, so you guys have, you don't have anything new over the weekend. We're going to start 6-3 together, and then you have your last video ever on Monday night.
Oh my god.
You guys, look at you guys.